Alright, let's talk OOP in Python. Object-oriented programming gets a bad rap sometimes. People think it's over-engineered or academic. But when you actually use it well, it makes your code dramatically easier to reason about, extend, and maintain. In this deck, we're not just covering the theory, we're going through the practical patterns you'll actually reach for when you're building real stuff. So before we dive into classes and all that, let's talk about the mental shift. Most of us start out writing procedural code, top to bottom, step by step. You've got your functions, your variables, and they're kind of floating around, loosely related. OOP flips that. Instead of thinking in sequences, you start thinking in things. Objects that own their own data and know how to behave. It's less like a recipe and more like a team of specialists, each responsible for their own domain. Okay, this is the foundational concept, and it trips people up more than it should. A class is just a blueprint. It's static. It lives in your source file. It doesn't do anything on its own. An instance is what you get when you actually call that class, like user Alice. At that point, Python allocates memory, runs your dunder init, and you've got a live object. The class is the cookie cutter. The instance is the actual cookie. You can make as many cookies as you want from the same cutter, each one independent. First pillar, encapsulation. The core idea is bundling your data and the methods that touch that data into one unit, the class. But the real power is information hiding. You're not exposing your internals to the rest of the codebase. Think about it. If any part of your program can just reach in and set a value to something nonsensical, you've got a data integrity nightmare. Encapsulation gives you a protective layer. You control how data gets in and out, and you can validate it at every step. Here's a concrete example, a digital save class. Notice the __ pin attribute. That double underscore prefix, which we call a dunder prefix, triggers Python's name mangling. Basically, Python renames it under the hood, so it's not directly accessible from outside the class. You can't just do safe.__ pin and get the value. Instead, you go through change_pin, which validates that the new pin is an integer between 1000 and 9999 before it ever touches the internal state. That's encapsulation doing its job. The data is protected and the interface is clean. Next up, abstraction. This one's about hiding complexity. The user of your class shouldn't need to know how it works, just what it does. You're defining a contract. In Python, we do this formally with abstract base classes, or ABCs from the ABC module in the stdlib. You mark methods as abstract, and any subclass that doesn't implement them will blow up at instantiation. It's Python's way of enforcing an interface. Less noise, less coupling, cleaner API. So here we've got an exporter ABC with an abstract save method. You literally cannot instantiate exporter directly. Python will throw a type error. But CSV exporter inherits from it and provides a real implementation of save. Now the beautiful thing is, the calling code doesn't care if it's a CSV exporter, a JSON exporter, or a PDF exporter. It just calls .save and trusts the contract. That's the power of abstraction. You program to the interface, not the implementation. Inheritance, the one everyone learns first and sometimes overuses. The idea is simple. A child class gets everything the parent has. So if device has a power method, phone inherits it automatically. No copy-paste, no boilerplate. You build specialized types from a general base. The concentric circles diagram here shows it nicely. Device at the core, phone extending it, smartphone extending that further. Each layer adds specificity without throwing away what came before. Polymorphism. The name sounds fancy, but the concept is beautifully simple, and it's basically baked into Python's DNA. The classic quote is, "If it walks like a duck and quacks like a duck, it's a duck." Python doesn't care about the type of an object, it cares about behavior. Does it have the method you're trying to call? Great, it works. This is called duck typing, and it means you can write code that operates on wildly different objects through a single, unified interface. No explicit type declarations needed. Here's the duck typing example in action. We've got a bird class and a car class, totally unrelated, but both have a move method. So we throw them in a list, loop over them, call move on each one, and it just works. Bird flaps, car drives. The loop doesn't know or care what type it's dealing with. This is why Python code can be so expressive. You write one loop, and it handles many types gracefully. That's polymorphism earning its keep. Last one. And honestly, this is the one that separates intermediate devs from senior devs: composition over inheritance. Instead of saying car is an engine through inheritance, you say car has an engine as an attribute. That subtle shift is huge. With inheritance, you're tightly coupled to your parent class. Change the base, and you might break every child. With composition, you can swap out the engine at runtime, inject a mock in tests, or upgrade behavior without touching car at all. Build with small focus, testable pieces, and compose them into something powerful.